So in this lesson we're going to take a look at three important properties for the log and exponential graphs. It's going to be the asymptote, the domain, and the range. So we're going to want to be able to answer these questions about log and exponential functions. To start, we're going to use graphs, and then we're going to talk about how we could use our knowledge of transformations and how we look at equations to do it. So let's start here by taking a look at the graph y equals 2x. There's an asymptote in this picture, so I'll draw it in for you. This is where the asymptote occurs, and that happens where y equals to 0. Now, if we look at the domain, just a refresher, those are the x values that we're thinking of that are permitted in this function. So it looks like I could pick any value for x and not have any problems. So this would be all real numbers. And of course we could abbreviate it like that. The range of values, those are going to be the ones above the asymptote. Remember, it can't cross the asymptote, so it'd have to be strictly above it. So that means it's going to be y greater than 0. Okay. Eventually we're going to have to be able to talk about this for any sort of exponential or log graph. So this one has some transformations applied to it. But we should be able to use our transformations knowledge to do that. This would be left 1 and down 4. So I could take the original set of points, which are here, and I could map them left 1 and down 4. Okay. So those points that I've now mapped, that's going to be the new transformed function. And of course you could always just substitute values in for x here, but transformations is something you should keep practicing because that is one of our topics in this class. So here is the transformed graph. And if I try to pick out those key features of the function now, I can see the asymptote down here at y equals -4. I can also see that the range, that's all values above here, are the values y greater than -4. Remember, it never touches the asymptote, so it can't be greater than or equal to. It has to be just greater than. And the domain, which is going to be, well, again, doesn't look like there'll be any problem. Any value of x that I put into the function here is going to give me a real value. It's going to be fine, so the domain will be all real numbers again. So now we're going to take a look at connecting those exponential graphs to the logarithms. And one thing we want to talk about first is when we go from the exponential function to the logarithm, that's the function to its inverse, we have to be a little careful here about how we deal with the base. Okay. So for example, any problems that we'd have for the base in an exponential function, and one hint that I'm going to give you is think about fractional exponents. Now, if you think about a number like, I don't know, let's try -1 to the x, you should ask yourself, would there be any problems here if I tried to graph this out? One example you might come up with would be something like this, because that is the same thing as the square root of -1, which would cause us some problems. This would not be a very good function to work with. So, so that's one thing that we're going to have to take into account here, that the base could not be negative. Now, there's a couple other parts that seem harmless, but it's going to cause problems when we go into the logarithm. So for example, if I was to take a look at the function 0 to the x, then it's easier to explain it with the picture. Here's the picture of that graph. And we remember that the inverse is the reflection on the line y equals x. So here's what the inverse graph would look like. This would be the log base 0. So the problem here is that this is not a function. It does not pass a vertical line test. There's more than one value of y for that value of x. So for example, if I was to say what exponent of 0, if we were trying to ask, log base 0 of 0 equals what? Well, it could be, log base 0 of, I don't know, let's say, yeah, that was actually correct, equals what? You could tell me, well, 0 to the 2 is 0. You could tell me 0 cubed is 0. You could tell me 0 to the 4 is 0. So there is no one value. There's actually an infinite number. We wouldn't be able to actually give an answer for this. So we want to avoid letting the base equal to 0 because there will be no logarithm for that. Similarly, we would also have the same problem if we were trying to talk about another graph. So this graph here, one to the x, will have the same problem happen. So here would be the inverse. It's a vertical line. It's not a function. It's going to cause us some problems here. So we don't want to allow it to be equal to 1 to the x either. So that gives us the list of restrictions that the base has to be greater than 0 and cannot equal 1. So those are some important things you'll have to keep in mind when we talk about logarithms. So let's take a look at what this graph actually looks like for a logarithm. To do the inverse, we'll start again with what you already know, which is transformations. So we could take some points, like for example, this would be a good point. Some nice easy ones to calculate. If I take their reflection, it's going to look just about like this. Okay. So this is the exponential. So this would be the log base 2 of x. Okay. So now what we'll talk about is, what are these key features on the log graph? Well, there's an asymptote here. And that happens when x equals to 0. The other way we could think about this is, here's the asymptote in the function. That happens when y equals to 0. And when we go from the function to the inverse, we're switching x and y. So that means we have y equals 0 in the function. That's the asymptote for the exponential. Then the logarithm will have x equals to 0. X and y get switched. And that'll happen everywhere else we would have seen this. So domain is x and range is y. So if the domain of the logarithm, if I look at it, it can't cross the asymptote. It's going to be x greater than 0. And if I look at the function here, that's y greater than 0. And that's the range. So the range values, which are the y values, become the domain and the x values in the inverse. Okay. And finally, same thing happens here. We'd have all real numbers. The domain of the function is going to be all real numbers, so the range of the inverse is going to have all real numbers. And you can see it in the picture here too. It's going to go down as far as we want along that asymptote, and it will eventually keep rising higher and higher and higher as it goes on, but it would be all real numbers for the range. Okay, so same idea. We may not be super comfortable yet with the log graph, but we should be able to talk about transformations. So this is left 1 and down 2. So if this was my original graph here, I can map these points again. That'll be 0, 1, 3, and 7, -2, -1, 0, and 1. So on the new graph, I would end up with, let's see here. Oops, I believe there's a typo there. That should be the log base 2, since we're clearly here in powers of 2. So 0, -2 should be there, and 1, -1, 3, 0, and 7, 1. So again, we're going to want to be able to talk about any old logarithm graph, not just the basic ones like this. We want to be able to use it for any function. So transformations can help us, because now my picture, I could see that there's an asymptote here at x equals -1. And I can also pick out my domain is where x is greater than -1. And that my range is still all real numbers. Okay, so we've talked about this one just briefly, but remember we need to state this, that if I'm going to go from this base and use it in the logarithm function, that the base has to be greater than 0, because otherwise it will not work in here, and that the base cannot be equal to 1 or the log is not a function. And that's the same reason why we don't include an equal sign here, because if it was equal to 0, the log would also not be a function. Okay, so we have to be careful about this, and we'll talk about it a little bit more just shortly. Okay, so let's talk about some shortcuts now. If we didn't have the graphs, how could we find the asymptotes here? So if this was our function and we wanted to change things around, let's talk about how could we find the asymptote now. So the asymptote is a horizontal line for an exponential graph. So if I'm moving that asymptote, it would have to be vertical, up and down. So for example, if this is my graph, put my exponential here, then if I move the graph over, nothing happens to the asymptote. It's when I move it up and down, shifting the graph up and down, that the asymptote will change. And the only piece that moves things up and down is here. And in fact, that's exactly where we find the asymptote. So if we wanted to find a shortcut, the asymptote will be at y equals to k. Now, if we wanted to find the domain, there's no problems with domain regardless of how we shift the graph left and right. It will always be all real numbers. Okay. The range, well, if we take a look at the exponential graph again, remember it's rising off that asymptote, so it's basically going to assume one side of the asymptote. It could also go this way, and in that case it would have to have a reflection in the x-axis. And if you remember from transformations, that means we'd have a negative sign in front. So if we wanted a shortcut for this, the way we could write down the range is y is greater than k, if no reflection. And y is less than k if there is a reflection. So just to be clear about what we mean there, for example, y equals negative 2 to the x plus 1 minus 3. Now let's go plus 3. That example would have a range y less than 3. 3 is the asymptote, and there is a reflection, so it will be less than. Okay, the graph will be pointing lower. In the logarithm graphs, if we wanted to find the asymptote, then we have to think about where the problems occur. So what we said was we couldn't have a situation where the value inside here was less than or equal to 0. We'd have a problem, because the exponential graph has to be bigger than or equal to 0 here. There's no way to make a number like, say, 2 to the x become negative. It doesn't happen. It won't work. So if we can't get a negative number out, we can't put a negative in for the log. It won't happen. So this is where we're going to find the problems, and the asymptotes, remember, they mark where a boundary happens. So the asymptote is going to be where x minus h equals to 0, because we don't want to cross that line. That's where problems happen in the asymptote. For the domain, again, it's the same issue. We have to make sure that any number we put into it is greater than 0, so x minus h must be greater than 0. And the range, no matter what we do, is going to be all real numbers. Okay. So let's take a look at how we could work some of these examples without having to do the graphs. It'd be much quicker to do this. So let's try here with 2 to the x plus 2. The asymptote, remember, is going to be, it's kind of like there's a plus 0. So there will be an asymptote at y equals 0. In this situation, the asymptote will be negative 2. And in this one, negative 12. So we can pick it up very quickly without having to do the graph. Okay. What about the domain? Well, we said that no matter what happens here, we can put in any value we like for x. It's all real numbers. The range, however, remember, we have to decide, is it going above the asymptote or below the asymptote? In this case, there's no reflection. So it's going to be rising, it's going to be getting bigger, so it's going to be y greater than 0, so larger than the asymptote. Again, there's no reflection here. It's going to be getting larger, so it's going to rise above the asymptote, so y will be greater than negative 2. This one does have a reflection. So there it is. The negative sign makes this graph flip. It's going to become very, very large as a negative. So it's going to be going below the asymptote. So y would be less than negative 12. Okay, so we're going to try the same thing using the shortcuts for logarithms. Finding the asymptote again, what we're thinking about here in the shortcut is where's the border? Where's the problem, the boundaries that could happen? That means x equals negative 3 is the asymptote in this case. This one is, there's maybe a tiny bit more work that we'd have to do. That means x will be 3/2. That's where I'll find an asymptote. Okay. And then the last one here, the boundary will be where 1 minus x is equal to 0. So that means x would be equal to 1. There's going to be an asymptote there. Okay. The domain, again, this is dealing with the boundaries that occur. We want to make sure x plus 3 is greater than 0. So that means x would have to be greater than negative 3. And 2x minus 3 would have to be greater than 0. So 2x would be greater than 3, and x would be greater than 3 halves. Okay. In the last example, 1 minus x has to be greater than 0. So if I keep this as negative x is greater than negative 1, when I divide by a negative, remember, be careful because you have to change that sign. So in this case, the domain is x must be less than 1. Okay, and then finally, the easy one for the logs. The range of values, no matter how we transform the graph, will take on all real numbers. So we'll just try a couple of extra questions here, provincial exam style that you might find. Knowledge that hopefully you can pick up from that lesson, but maybe you need a little refresher. It says that this passes through the point 3 and 216, so that's x and y. So if we wanted to find the base, that means 216 equals a to the 3. And if we're trying to figure out what this is, if we raised both sides to the 1/3 cube root, then that means I'll end up with a is 6. Again, this will be x value, this will be the y value. So if we recognize that, this is what we're trying to figure out. And I would probably rewrite this as a to the 8 equals 256. It's a little easier to solve for. Then I'll do the same thing. If I take the 8th root of both sides, I'll get a equals to 2. Okay, for log base 5, there's some clues here. It says it has an x-intercept at 5. So we should remember when you have an x-intercept, y equals 0. So I'm actually being told there's a point 5, 0. And we want to figure out the value of k. So that means x equals 5, y equals 0. And remember, a logarithm is always asking which exponent I'm dealing with. So we could rewrite this as an exponent, and it would probably be easier to solve. And of course, this time it's not so bad. It's going to be 1 equals 5 minus k. Or if I rearranged this, k plus 1 equals 5. And k equals to 4. Okay. Another thing we should be able to do is find the intercepts. So for the x-intercept, that means y equals to 0. So to figure out the value of x, I'm going to put in 0 for y. And try to rearrange this. If I rewrite it as an exponential, that means 9 equals x plus 1, so x would be equal to 8. And if I'm trying to find the y-intercept, that means x equals to 0. So this one will actually be easier. Log base 3 of 0 plus 1 minus 2. So this will be y equals log base 3 of 1 minus 2. So which exponent of 3 gives me an answer of 1? Well, that exponent would have to be 0. So y equals to negative 2. And we'll repeat that with the exponential. So for example, this time 3x plus 1 minus 9, I'm going to have x-intercept y equals to 0. 9 equals 3 to the x plus 1. So if we're doing this like the exponential equations we've looked at, let's see here, so then that means x would be equal to 1. And I'm sure, you know, at this point you might have common sense enough just to guess that it was x equals 1. If I want the y-intercept, that means x equals 0. So y will be equal to 3 to the 0 plus 1 minus 9. Y equals 3 to the 1 minus 9. So y equals 3 minus 9, which is negative 6. So again, there's a lot of key features which, you know, usually you think of a graph for intercepts and things like that, that you don't necessarily need to resort to the graph. You would be able to do this with algebra. Okay. So the last thing that we want to talk about is, now that we've said the properties between these two graphs, we'd like to be able to convert from the function to its inverse. So let me show you here the process. To find the inverse graph, first step is still the same. We're going to switch x and y. So to do that, x equals 2 to the y plus 1. Isolate the exponent. So what I mean is I want this to be all by itself. I don't want anything near it. So I'm going to, for step 2, make this x minus 1 equals 2 to the y. And then for step 3, I want to rewrite this in logarithmic form. So this is log in base 2 of x minus 1 equals to y. And that's the inverse function of this. Okay. Now, we'll try it again here. This time we'll do logarithms. The process is the same. So switch x and y. Then what I want to do is I want to keep the logarithm all by itself. So this is what I'm trying to keep the logarithm by itself so that I can rewrite this as an exponential. So this will be x plus 1 equals log base 3 of y plus 2. And to rewrite this as an exponential, that would be 3 to the x plus 1 equals y plus 2. So I would probably write this as y equals 3 to the x plus 1 minus 2, just by moving the 2 to the other side. Okay, so a couple inverses for you to try. You may want to pause it and see if you can do this one on by yourself, and then take a look at my solution. So I'll try this one here first. Step number 1 again is to switch x and y, same as it is for every inverse we've talked about. Step number 2 is to get the exponential all by itself. And then step number 3 is to rewrite this as a logarithm. So this would be the log base 3 of x minus 2 equals y minus 6. So y equals log base 3 of x minus 2 plus 6. Okay, so for the next example, I'll do the logarithm here, and that'll be x equals log base 5 of y plus 4 minus 1. Get the logarithm by itself so that I can rewrite as an exponent. And now I'll rewrite this in exponential form. So y will be equal to 5x plus 1 minus 4. So if you had no problems doing those two, that's great. You probably want to go ahead and just finish the last two on your own. Otherwise, you may want to take a look over it, pause it, and then try this one here, these next two examples again to see if you're getting the hang of this. So I'm going to go ahead, but you may want to pause it again. If I rewrite this and then isolate it, and rewrite it as a log, then that would tell me the inverse is log base 5 of x plus 4 minus 1. And finally, x equals log in base 7 of y minus 1 plus 3. X minus 3 is log base 7 y minus 1. Now that it's isolated, I can rewrite it. So the inverse would be 7 to the x minus 3 plus 1.